All right, hello there again. Okay, so at this point we are on to acceleration. Now this will actually be the last topic of the first half of physics. So after acceleration, you guys will be having a kinematics test. And then we'll move on to part 2. Okay, so in this section, we're going to be able to understand the relationship between velocity, time, and acceleration. So there will be a calculation and just kind of understanding some concepts. Now, we've chosen to actually remove the velocity time graphs. They're just a bit confusing, and we figured with our current situation that we will take those out. But be aware, if you move on to grade 11 physics, they'll review that for you, but it will be in that section. Okay, with acceleration, we've all probably, come across this in our daily life. We know what accelerating is. It can be speeding up or kind of slowing down. So if you think about a car, trying to accelerate after a green light, this is now non-uniform motion. So uniform motion is about traveling at a steady speed. So obviously if you're changing your speed over time, that's non-uniform. Acceleration is a vector, which means direction is important. And the definition is about it being a change in velocity over a specific time interval. Okay? So again, we're thinking of speeding up and slowing down. Slowing down can still be called acceleration, but it would be negative acceleration. All right, so what is our formula? Okay, A stands for acceleration. That arrow goes on top of the A. It should be there because it's a vector. Then it's about taking the change in velocity and dividing it by the change in time. You're going to need to know both of these kind of scenarios. The V2 minus V1 or VF minus VI, final minus initial, sometimes because you're accelerating, you're going to be dealing with the initial velocity as well as the final velocity to indicate that change in speed. So that's where that one will come in, okay? So it is important to remember both of these. But the shorthand of this would just be A equals V over T. All right? Or I probably commonly will go do the VF minus VI over T because I find that final and initial is more clear than 2 and 1. All right, our units are typically going to be in meters per second squared, all right? Because velocity is in meters per second and we're dividing by time, it's meters per second squared. That square does not actually mean you calculate into squaring the time. It's just because of the way the units work, all right? Because it's meters per second divided by second. The units are meters per second squared, okay? Now, we're typically going to be dealing with time in seconds, but if you are given velocity in kilometers per hour, you may have to convert it. Now, in terms of understanding acceleration, if I were to look at what that means, acceleration is velocity over time. So velocity on the y-axis, time on the x. Now, really what's happening here is if I look at kind of each second, the person's speed is increasing at a rate of 2 meters per second each second. Okay, so they're going 2 meters per second faster every second. All right, that's what the kind of meters per second squared means. Just a thought. All right, so with acceleration, because it's a vector, we've already discussed that it can be positive or negative. Now, often in physics, we then use positive and negative signs for that. But positive and negative can also indicate simply direction when you're talking about velocity. So velocity negative might mean simply moving in the opposite direction. It doesn't necessarily mean slowing down. So in order to figure out if an object is actually speeding up or slowing down, you need to consider the sign for both velocity and acceleration. Okay, so the sign on acceleration tells us the direction the acceleration is acting, but the sign on velocity tells you kind of the direction the object is moving. So positive acceleration does not necessarily always mean that the object is speeding up. Sometimes it could be that they are slowing down, but in the positive direction. So ignore everything I just said for a second. Let me just simplify it. if we look at this table, a positive velocity could mean, so we have, velocity here, acceleration, and what that really means. Okay, if my velocity is positive, and positive is to the right, and my acceleration is positive, which means to the right, what's happening is the object is moving right, according to velocity, and speeding up. Okay, but if my velocity is positive, indicating the object is moving right, but my acceleration is negative, that means they are moving right, but slowing down. Okay, because the acceleration is working in the opposite direction of the movement. So here's the summary, all right? If you look at the sign of the velocity and the acceleration, if they're the same, either both positive or both negative, that indicates the object is speeding up, okay? Because the acceleration is acting in the same direction as the motion. But if the velocity and acceleration have opposite signs, then the object is slowing down because the acceleration is opposing the direction of motion. Okay? Most of the time it will be fairly clear in the question, but this might be more complicated in grade 11. So matching signs, accelerating, opposing signs, slowing down. All right, let's get into then the examples. So it's very important that you follow my model of how I kind of write down all my information, show my work, because especially if you're planning on moving on in physics, they're not going to accept just answers. All right, so Jasmine is learning how to use a bow and arrow, and her instructor tells her that the arrow is traveling at a velocity of 139 meters per second for 0.15 seconds. What is the average acceleration for the arrow? It is very important in science to try and, when you're answering a question, try and highlight or underline the important information to pull out. All right, so I like to summarize what I have. So my velocity is 139 meters per second. My time is 0.15 seconds. You need to be able to recognize the kind of value by the units, right? So I should be able to know that that's time because that's in seconds. I'm asked to solve for average acceleration. So this leads me to writing down my formula, where acceleration equals velocity divided by time. So I plug in my numbers that I know, 139 meters per second divided by 0.15 seconds. Okay, I calculate that. And that leads me to 926.6 repeating, but I'm just going to write 0.67. And my units are meters per second squared. All right. Now, there was no real indication about what direction everything was traveling, but this is going to be positive. Okay, so my calculation turned out positive, so it's positive. And that's my answer. If you're not really given any sort of direction, you don't need to worry about it, but if the velocity has the direction, then you'll have to include it. All right, example 2. A longboarder's velocity is positive 1 meter per second. After 3 seconds, his velocity is 6 meters per second. What is his acceleration? All right, so we're still solving for acceleration, but now we see that I have 2 different velocity values. My time is 3 seconds. So you have to kind of consider now initial and final. So if we look at this question again, the longboarder is starting at 1 meter per second. And after 3 seconds, so later or final, it's at 6 meters per second. So that's the data I've gathered. This is where now we're going to be using our other kind of version of the formula here, where VF minus VI divided by T. That simply is calculating that kind of change in velocity, or that delta V. So I plug in 6 meters per second, subtract 1 meter per second, they're both positive, over 3 seconds. So I calculate that, and that's going to be 1.67 meters per second squared. And again, positive. All right. Hopefully this is pretty straightforward so far. Got 5 examples total. We're on to number 3 here. A ball is rolling along the floor and comes to a stop. So that would indicate that the final velocity is 0 after 2 seconds. The ball's acceleration is negative 4.6 meters per second squared. What is the initial velocity? All right, so we're going to have to definitely do some manipulating and some solving here. Let's gather all the data. Final velocity is 0 meters per second. Time, 2 seconds. Acceleration, negative 4.6 meters per second squared. Initial velocity is what we're after. So I'm still going to be having to use this formula. I plug in my numbers, and it is important to make sure you don't forget about that negative, right? Direction matters. VF is 0 minus VI is what we're solving for, divided by 2 seconds. Okay, so now we start to kind of manipulate and solve for that VI. The first thing I'm going to be dealing with is the time. I'm going to multiply by 2 seconds on each side. This is that algebra, right? You do the opposite operation and you do the same thing to both sides. That cancels. Now I'm going to actually do that math there before I move on. So 2 times negative 4.6 gives me 9.2. So I'm just going to write that down. Positive, that would be negative 9.2 equals 0 minus VI. All right, I'm just taking out the units just to show it a little bit simpler right now. Now, what I'm going to actually do is move over the VI first in order to get it to be positive. So I'm going to do the opposite operation, which is add VI to both sides. Okay, and those cancel. All right, let's look at what we've got now. We have VI plus a negative 9.2 equals 0 so far. Now I have to move my negative 9.2. To do that, I'm going to add 9.2, add 9.2. So VI equals 9.2 meters per second. All right. So now what I like to do is just, and this is positive, double check my work here. So I'm going to go back to this formula and I'm going to plug in my initial velocity and just double check that the acceleration works out. So that would be going 0 minus 9.2 divided by 2, and I get negative 4.6, which is my acceleration. All right, so that worked out. Okay, number 4. A propeller airplane is flying at 23.6 meters per second north and begins to accelerate for 13 seconds. If its final velocity is 43 meters per second, determine the acceleration. All right, so this one should be fairly straightforward. Initial velocity is 23.6 meters per second north. Time is 13 seconds. Final velocity is 43 meters per second. And we are solving for acceleration. VF minus VI over T. Okay, my VF is 43 meters per second. I'm going to guess that that's north, but it doesn't say. Subtract 23.6 meters per second north divided by 13 seconds. Okay, give me a second. Okay, that equals 1.4923, but I'm just going to, most of the time we can just leave it at 2 decimal places. As you move on in science, you'll learn about significant digits, but we'll just leave that. My units become meters per second squared, and because my velocity was north, my acceleration is north here because it's positive. All right, last one. A bus with an initial velocity of 12 meters per second accelerates at 0.62 meters per second for 15 seconds. What is the final velocity? Okay, so this one's going to be requiring some manipulation. VI is 12 meters per second. Acceleration is 0.62 meters per second squared, and time is 15 seconds. Okay, we start with our formula. We plug in our numbers. All right. Okay, step one, you always have to deal with that time first, all right? We can't just leave it down there, get it out of the way. So opposite operation is multiplication, multiply by 15 seconds to both sides. Okay, I'm going to do that math on the left. So 15 times 0.62 is 9.3. So 9.3 equals VF minus 12 meters per second. Okay, I'm solving for VF, so I need to move the 12. So I add opposite operation, 12 meters per second. And then I do that math. 9.3 plus 12 is 21.3 meters per second equals VF. That's what I'm left with. Okay, always good to double check when you're dealing with these with longer manipulation. So 21.3 subtract 12 divided by 15 equals 0.62. So that worked out. All right, there you have it for acceleration. At this point, you're going to be working into your workbook, doing page 19. Number 1 through 6 is what is required there. Okay, 7 through 10 is extra. All right, good.